Okay, good evening everyone. So it seems Can you hear me? Yes, I think you should be able to hear me. I just need to scroll down to see if my microphone actually shows any activity, but it seems everything is fine. So officially, good evening everyone. And yes, today's topic is going to be hash extension attack. I guess I'll do some theory / practice and then show you why do we care, basically. Today's moderator is not KrzaQ, it's actually Foxtrot Charlie, so here is his nickname. If you have any questions during the stream, basically do let Foxtrot Charlie know, and he will be able to let me know that there is a question using actually confidential methods. Yes. So, if you are, by the way, on our IRC, and I do encourage you to join our IRC channel on Freenode, then you can just type !Q and then the question, and it will also get passed to me. So that's that. Apart from that, let me think. This is Foxtrot's website. Wait. Okay, I thought something didn't work with my zooming, but like I didn't load the macros, but now it's here. Yeah, you can, it's really easy to remember the name, so do check it out. There are some posts there, probably. Yeah, do ask Foxtrot Charlie why he isn't updating it, so he will, you know, be motivated to maybe put something new. Or maybe I should, I guess, yeah, maybe I should post new missions, and there is actually no mission today because I basically just got back from work, and even if I could have it ready, then I wouldn't be able to hook it up in time, so sorry about that. Hopefully next week, or hopefully tomorrow if you are joining me on our Polish live streams as well. So another thing, as you may know, I'm co-organizing a conference in Poland. This will be the third year the conference will happen. It's in Warsaw in November, and it's mostly in Polish, but there is a simultaneous translator if you actually speak English. Then you know you can just hook your plug in your ear, and you will be able to hear the translator translating live whatever the speaker is talking about. Now, I'm mentioning this because Google is actually sponsoring the conference this year with grants, basically. So there are 10 grants for I guess university students mostly, but not only. Basically, you have to apply, and there's the long form in English to fill out, and if you are selected, and 10 people will be selected, then you get free travel to Warsaw, free conference ticket, and lodging as well. So do try it out if you're interested. And there's if you go to my blog post, like actually both the English and the Polish side have the same post about this. So there's that. Because, well, you probably know the link to my blog, but I will give you it anyway. I should give you the link to Foxtrot's blog as well. Here we go. Cool. Apart from that, you might know that I have this /n for notes, where I note things for myself mostly, but you are free to look there as well. And for example, I have this PHP quirks thingy, and I did update the section on PHP extensions, as in which extensions the default configuration of PHP and Apache, or whatever the default configuration on a given operating system is, allows or actually treats as a PHP script and executes it. And this is important if you, I guess, if you do like, you know, pen testing or CTFs, and you have an upload vulnerability, so you can upload a file and it's mapped using www, and PHP extensions blocked, for example. So this is blocked. But in some, like for example, on the newest Ubuntu or Debian, like with PHP 7.2, there is this .power extension that you could use, or PHTML extension that you could use as well. So yeah, it's basically for bypassing blacklists. It's not a huge deal, but yeah, I decided to note this down because some of the extensions which are on the list did surprise me on some CTF, and I prefer to, you know, just have this handy. So again, it's like for exploiting a vulnerability, you would already need to know. Apart from that, there's one more thing, one channel actually I wanted to tell you. It's on my, where is it? Here we go. KrzaQ started doing videos on YouTube, and actually there is one where he explains in 10 minutes the details, the technical details on how to steal messages from Signal, and he basically explains the CV as in this vulnerability which has been granted this CV identifier. If you don't know what CVE is, it's basically common vulnerability enumeration. It's basically like a number consisting of a year and an identifier of a vulnerability, and usually, well, historically only like good vulnerabilities got it, as in, you know, something which was high or critical. And nowadays I think it's just an enumeration of most of the vulnerabilities out there, which is a good thing, I think. So it's a huge database of vulnerabilities, and yeah, KrzaQ is explaining this vulnerability. I'm not sure if he's actually the person who found it or if he's just explaining, but well, whatever. Here we go. I'm going to give you a link. Do actually subscribe to KrzaQ's channel, because he, like, to motivate him to do more videos, he has like only 306 subscribers. I don't even, I have no idea. Anyway, I don't even, yeah. So to motivate him, do subscribe to his channel as well. Maybe he will do more videos in English. Do tell him that you want videos in English. Otherwise, he might do them in some weird language like Polish or something. As I do. Anyway. Yeah, I think that's what I wanted to tell you today. So, as usual, let's start the topic of today's stream like a quarter past. So we have 8 minutes to kill, basically, to use for something else. So I guess if you have any questions, we can do them now. And 15 past, I will start the topic, which again is hash extension attack today. There's already, by the way, the topic for the next live stream is going to be address sanitizer internals. So I'm basically going to try to explain / figure out how does address sanitizer work. I do have some historical knowledge on how it works. If you're Polish, actually Mateusz Jurczyk has written an article about its internals. It was in one of the older Programista magazine issues. And I'm actually quite curious how it works now. And yeah, we can take a look together, and we'll try to figure it out. I'm not saying I'm an expert on the subject, because I'm not, but I should be able to figure out during the 2 hours of a live stream on how it works. Oh, one more important thing. Google CTF. It's going to start this weekend at, I think, midnight UTC, which means it's in Zurich is going to be, in like Central Europe, is going to be 2 a.m. on Saturday. And it's going to be 48-hour ranked team CTF, and do expect fun tasks. And there will also be a beginner's track. So if you're new into CTFs, you're kind of scared of usual ranked CTF tasks, don't worry, there will be a whole set of tasks for beginners, and do check it out. Yeah, I guess you can look on ctftime.org to find the link to the website, but let's do that just for the sake of killing a few minutes. Yeah, here we go. Google capture the flag. And yeah, like this is basically the qualification round. So if you qualify, then there will be, in the autumn, there will be finals, and the finals will have monetary prizes as well. Apart from that, the qualification round will actually have a competition. Let's call it a competition for best write-ups. So 32 write-ups will be selected and awarded from 100 to 500 USD. So do participate in this as well. Okay, what did I want to click? I wanted to click this. Yeah, I guess you can create a new team right now, and that's about it. What you can do, but the website will start on well, as soon as the CTF starts, basically. So that's that. Let me maybe give you a link to this. I fully encourage you to participate. There will be some challenges from me as well. I will be on IRC some time supporting the players, so it should be fun. Cool. Okay, questions. Let's see if actually, yeah, this works. No, wait, this works. Yeah, because I usually have questions displaying there, but last week it didn't work for some reason. I wanted to debug it, and I went to like the next day, right, on the Polish live stream, and it just worked, like out of the box. I don't know. Let's see if it works today. There are some questions. It works. Okay, perfect. Whatever. I don't know. Okay, there's a question. So, before we start, what do you think about the GDPR new laws? I need to take a deeper look into them. They sound interesting in a way that, you know, something which was like really wild, wild west, now there's a set of policies to govern it. And a lot of, well, currently, you know, everyone is probably getting a lot of emails where companies would like us to accept a GDPR policy which they had to introduce. And I did see some spam as well, where I get like some random emails from companies I never had any interaction with saying that, yeah, please accept the GDPR policy because otherwise you will lose access to your account on blah, blah, blah. So that's quite funny. I mean, I guess, you know, folks doing shady stuff always will find a way to use a situation. Apart from that, I don't really have a huge comment. You know, it was a huge commotion in Europe, but I didn't look into it too much because, well, I am not a company, and GDPR is mostly about companies. So yeah, I might have a comment about it later on. My apologies. Okay, another question. Do you know any large-scale mesh networks like Hamnet? Not really. What's a... Okay, and this is where everyone finds out I'm actually a noob. What's a mesh network? Or what's Hamnet? Ham sounds like amateur radios, actually. Well, this looks like normal internet. Why is it different from non... Why is it like different from something else? Hamnet Shakespeare. I'm pretty sure this is not the Hamnet I wanted to. Nope, Wikipedia doesn't have anything on it. So, Noodly, if you have a good link on that, please do let me know. I'm quite curious. What do you have in mind? Why do I have a certificate named Gunveil Caldwin that expires in 2097? What is it? Why do you have a certificate like that? I don't know. Why do you have a certificate like that? Where did you find the certificate? Is it on my website? If it's on my... let's see what certificate is currently on my website, because I still have the self-signed one. So yeah, let's go. High-speed amateur radio multimedia network. That's okay. That's interesting. Yeah. Okay. Let's proceed and let's see what certificate is this. Oh, I cannot. No, I can't proceed. But my server is super slow as usual. Okay. And we go to security. We don't want this. View certificate. Yeah, it's a self-signed certificate. I used it for some experimentation, basically, and some other stuff. But given that, yeah, HTTPS is a must now, I'm going to probably switch the server to a proper certificate around next week. Yeah, but it's a self-signed certificate, so just ignore it. Which means I generated it on my computer. It should not be trusted by any means. Will you ever make a guide about virtual function C++? A guide about virtual function C++? I don't know. What kind of a guide would you be interested in? Also, is virtual function something else than virtual method, like function method? Do let me know. I'm quite curious what do you have exactly in mind. Or is it like a, I don't know, beginner's tutorial for like how do you do virtual methods in C++? Maybe this is something you're interested in. Okay, 15 passed, so I guess we should get started, but there are 2 more questions. I'm going to finish it. When I read about Linux, many times there is this argument that it's safer than Windows, but not really. Why is it safer? Why would Linux be safer? I'm not sure it's safer. It was safer like back in the old days. Currently, I actually feel like Linux is lagging behind in like mitigations and so on. So yeah, I guess the usual argument is that it's safer because it's open source, so everyone can look at the code, but it's not about everyone looking at the code, it's actually about somebody looking at the code. So there's a difference between everyone can and somebody actually is. And yeah, like people do look at the code in Linux obviously, but they also do look at the code of Windows. And Windows, in Windows 10, especially Windows 8 and like Windows 7 and so on, they introduced a lot of they introduced a lot of mitigations, both in kernel land and in user land, which are not yet there in Linux. So I'm not sure the argument is current. Yeah. My take is like both operating systems, like both the open source one and the closed source one, have their vulnerabilities, and in the last year have been pwned by some vulnerabilities. So yeah, if I wouldn't say like one is safer than the other. Genway is alphabet D. Not sure yet, but the language D is not in my alphabet yet. Again, are you going to make random question stream like you did on your Polish channel? Sorry. Ah, my god, I probably should get some. Oh, I have some water. Okay. And I have tea as well. Anyway, yeah, I might make. So it's like this. I make a random question stream channel, live stream, every time I don't have a good topic to do. So if you have any questions, just put them out there, like send them to Foxtrot Charlie, because I am going to stay today, you know, after the stream and answer them. And yeah, so if I don't have any good topic, or people would actually like me to make just a stream without any topic, it's just where we chat with each other, well, I answer your questions, I guess, because, well, for this is a technology which doesn't actually allow us to chat too much. So yeah, if you'd like me to do one, then do let me know. And yeah, and I guess we can get going. Cool. Well, I think two more questions. I'm going to look at them, well, later on, right? And we can start with hashes. And yeah, I'm going to start with explaining what is hashing. Like if you never implemented MD5 or CRC32 or whatever, you probably don't. It might be like a black box in your mind, right? But oh, it's a function, and you put data in the function, and like magical strings come out. But how does it work internally, right? That's the question, and that's, you know, the devil is usually in the details. So let's find it out. I'm going to create a really well-named file called ASDF. Oh, I'm in the MD5 directory. I don't want to be an MD5 directory just yet. Okay, asdf.py, as I mentioned, let's run a console. Here we go. So let's create a hash function. And usually there are, okay, so I guess everyone knows this, but a hash is basically a checksum of data. So you grab data of any size and you then do some mathematics on it, and what you get out is a string which is well, a number, which is always the same size in terms of normal classical hashes. I'm not going to talk about hashes which might be larger depending on the data size, because those also exist. So yeah, and then just looking at the hash, the idea is that if you take 2 hashes, then with certain probability, the data which has different hashes is like differs a lot or a little. So if you want to, basically, if you have a whole whole directory of files and you want to find 2 identical files without comparing each other, because let's say all the files are 1 gigabyte and you don't want to compare this file with this one because it takes time, and then with this one, with this one, with this one, what you want to do is you want to calculate a hash of each of the files. So you take the 1 gigabyte of data and calculate a hash, which might be you know, a shorter string. And so let's do just that. Okay, so this is, for example, a hash, like SHA256, SHA256 in this case. Yeah, and then you take these hashes and you compare the hashes against each other. You might want to use some, like, I don't know, a set to do that or whatever, but it doesn't matter at that time because comparing 2 hashes is really fast. Now, if you have 2 hashes and they match, then with certain probability, the files are equal. Like, the data in the files are equal. But the probability is not guaranteed because, well, something exists like a hash collision, which means that there might be 2 files which are distinct, which are different, but they have the same hash. Yeah, it's fully possible. And it's in the infinite number of files of a given size, well, almost infinite number of files in a given size. If the size of a file is larger than the size of a hash, there will be collisions. That's granted. There is no other way to do it, and I will also show you why is that. So yeah, that's basically it. Now, I'm going to write a really simple implementation of a stupid hash. Let's call it stupid hash because it will be a stupid hash. You usually in the hash interfaces, on the low level, you have 3 functions. One is initialize, which initializes the hash. I'm going to use just like the constructor here. Let's make it a little bigger. The second function is update, where you put some data in the math, and the math does like plays with the data, and then finalize, which basically gives you the hash, and maybe does something else as well. We'll get to that, but finalize is actually really important in today's stream. So okay, this will be just initializing something. Let's assume that we have a register which is yeah, like an initialized to 42, because why not? Most of the hashes we use today have a set of registers. The registers are of a given size. Let's assume that our is 8-bit, because why not? And just to make things easy, the registers are usually way larger. Like, for example, SHA256 has the registers of a size 256, I think. Hence the name. Though, yeah, anyway, so yeah, that's about it. And now we need an update, a function which we will put the data in, and it will calculate the hash of the data. So there will be data, and the update can be, by the way, called multiple times. So it shouldn't matter if we do like blah blah blah, like object update AAA, or if we do object update, like, and this is a separate call, update A 4 times. The hash should still be the same at the end. So it doesn't matter, because it basically is supposed to work stream-wise, as in the classical hashes, which today's stream is about, work stream-wise, as in they process byte by byte. This isn't fully true, but let's assume that it is true for the sake of the discussion. I will later get back to this and tell you that it wasn't true, but whatever. And yeah, let's do basically for each character inside the data, the character, we grab the ASCII code of that character, and then we, I don't know, XOR. Yeah, let's XOR the register with it. So this way we are basically guaranteeing that the register will be 8 bits, because this will never be larger than 8 bits. But let's maybe do it even in an even worse way. Let's use adding, like sum, instead of XOR, and now we need to actually do this to make sure that the register is kept inside 8 bits. FF is basically, you know, just 8 ones set, which means if I do a mask with it, and then everything up above these bits, which here are zeros, of course, is going to like be removed and zeroed out. So only 8 bottom bits will be left. And this is something I need to do in Python. If I would be programming in C, I would just use unsigned char type, and it would be done automatically. Yeah. Okay. So this is it. Now finalize. And in finalize, I'm not actually going to do anything. I'm just going to return it. And the thing which you return is usually called a digest, I guess. So I'm not going to do anything in finalize, but there's going to be this digest thingy which returns the result, and the result is R in our case. Let's make a character actually out of it, and usually implementations might have also like hex digest, where what you return is actually like, well, the same thing like digest, but actually encoded as hexadecimal. So this is a really stupid hash. You must agree with that, because it is. Therefore, let's use it. So stupid hash, let's create it. Now let's update it with some data. Update AAA, and let's print the result basically. So finalize it. Finalize is not going to do anything, and let's print the hex digest of it. Okay, and update self. Yeah, visual problem. That's okay. Here we go. Finalize, how did I save it? I did. Finalize takes 2 arguments. Finalize doesn't take data. And global name digest is not defined because this is self digest. Okay, no, that's fine. Okay, yeah, and this is what we got. 2e, and this is the hash of this data. Now I did mention at the beginning that it shouldn't matter whether I do like pass all 4 a's at once or pass them one after the other. It should still give me the same result, and that is actually the case, as you can see. So yeah, this is basically how hashing works. Now, I did mention that there are collisions, and this is quite obvious if you think about it, right? The hash, this internal hash, is like only 8 bits, right? So, which means that if we have like only one character in the input data, let's do only one character, then in the set of all 1 characters, like single characters, in this function, there should never be any collision. Because whatever we put here and add it to 42, right? Whatever we put here and add it to 42, which is already in the register, well, the result will be always different, right? Well, it doesn't matter if it's truncated to 8 bits or not, it always will be different because 0 added to 42 is 42, 1 added to 42 is 43, and so on, so it won't matter. That being said, if you start thinking about 2 characters, then, well, obviously, you start getting collisions. For example, let's display the hash for BB. And now we actually know how this stupid hash works because it just does additions, right? So B, as you know, is 42 hexadecimal, right? So 42 plus 42 hexadecimal, that's well 82 hexadecimal, right? Let's just do this is hexadecimal, just remember about it. It's 84, right? Well, same as in decimal, that doesn't matter. Now, actually the same result we would get if we would add to 41 43, right? It's still 84, and like 43 plus 41, so we already know that there are several collisions. How many collisions are there, you might ask? Well, we would have to basically increment this all the time by 1 and decrement this all the time by 1, and until they, you know, overlap and so on. So this gets to 0, then it starts again at 255, and this gets to 255 at some point a little later probably, and we like go around with 0 again. And well, there are only 255 possibilities here, which means that we have 255 collisions. And this actually makes sense because the internal register, if you think about it, right, it's 2 to the power of 8 possibilities. Now, this data here, like 1 byte, only 1 byte also has 2 to the 8 possibilities. So basically we already like occupy the whole possibility space. Now, if we have 2 characters instead of 1, then this isn't 8 anymore, this is 16. And which means we have each position, assuming the distribution is like is regular, is okay, and nothing is wrong with is linear. That's what I was looking for. Yeah, so assuming no, it's constant. The distribution is constant. Anyway, the distribution is like this. So assuming this, for every hash result, we have 2 to the power of 8 states collisions, and so on. So we had like 3 positions here, that would be 2 to the power of 24, which means we have actually 2 to the power of 16 collisions for each byte, which is quite obvious, but I wanted to get it out there. So now let's. There's one more thing about hashes. So there are kinds of hashes, right? There is like checksums, like for example CRC32. It's or the whole CRC family actually. It's not supposed to be secure in any way. As in, if you do a CRC of something, it actually already leaks your data. Like having the hash itself, I think you can get a couple of bits of the original last character which was fed into it, maybe an 8 bits. And you can probably reverse it easily without doing any brute forcing. So yeah, it's not a secure hash, but it's a fast one. And additionally, it allows you to basically see if anything was modified. A good hash, if you change 1 bit in the data, then at least like I think like 50% of the bits in the output data should change as well. And that's cool because that way you can easily spot if even 1 bit changed in the data. So this is good if you are, for example, sending data from, you know, over a network, like TCP, for example, or IP even have a hash of the data, right? So yeah, so like, you know, when the data reaches the other side, then the other side will be able to tell you that yeah, the checksum matches or it doesn't match. If it doesn't match, it doesn't mean that the data arrived correctly, obviously. It means that it arrived correctly or there has been a collision. So the data changed in a way which actually made the hash be identical, but the data has actually changed. I guess if you're trying to download something over a really, really bad internet and it's over HTTP and the download is successful but really slow, you might still find out that the file is actually corrupted just because that, like the packets on the network were corrupted, but the checksum was good because collision. Yeah, so but going back to CRC, basically it's a reversible hash, which means that knowing CRC is you can probably get a couple of bytes, some bits from the original data quite easily doing some basic math. Now, there are some, well, usually you don't want this. For example, if you are hashing passwords to compare them, so you have like hashes of passwords in the database, because when somebody is logging in, they do type the password, you hash the password, and you compare the hashes, right? So you know that the password was typed correctly. You don't want anyone to be able to take the hash and say, oh, it was this password, because that's actually called the pre-image attack, by the way. The pre-image being the thing which was, well, originally passed to the hash. Now, yeah, basically you keep the passwords in the database hashed because if the database is stolen, you don't want the passwords to be actually known. And if the password is good and the hash is good and used correctly, then that should be fine. By the way, I don't want to get into the topic how you should correctly store passwords in the database, because that's a really long discussion, but basically encrypted, hashed, and using some really, really good slow hashes, probably salted as well, is the way you want to go. Cool. So, oh, by the way, and you don't want to give access to the database to anything. Like, you want the database to be able to tell you if the hash which you give it is correct, or the password which you send it is correct, and change the hash, but you never want the database to provide anyone the ability to read the hash. So yeah, but that's another discussion. Let's not go over today. Okay, so yeah, so then we have like the more secure hashes, which is like, for example, MD5 or SH8256. Now you're going to probably say, no, MD5 is already broken, it's not a secure hash. Yes and no, it has been broken to a certain extent. For example, if I give you a hash, there is still no good way to reverse it. So even if I give you a hash, which is like, let's say 16 bytes, like 16 character password or something, then there is no fast way to know what 16 characters were the pre-image of that hash. MD5 is still not broken in that way. That being said, there are other ways MD5 is broken. For example, if you have some data and you can modify part of the data, like for example, add something at the end of the data or at the beginning of the data, then you can easily create two files which will be different but have the same MD5 hash. So the collisions are actually something which MD5 is broken with, and that's actually super fast as well. The SHA is like the current standard which folks use, I guess, nowadays. So yeah, so this is like the second property basically of a hash. Now, how hashes are used, I did mention already that is for storing the passwords in the database or for like comparing large files. Now there is another way in which the hashes are actually used for, and that's it's called HMAC basically, which is hash-based message authentication code, which means we have a message, something which is public, like I don't know, public message. Now this message is actually, as I said, it's public, but and we send it everywhere, and our system gets it back from the user. For example, we send it to a user and then we get it back, but we don't want it to be tampered with. We don't want the user to actually change the public message in any way, because, you know, we send the user public message and tell him, yeah, keep that and send it later to us, and the user just changes it to like, I don't know, public something, right? That doesn't matter really. And then we might trust it. I will show you examples in a second, by the way. Now, there's a question related to the stream. Is SHA1 secure? SHA1, is it secure? So SHA1 has been proven to be broken in a way that you can have two files which are of distinct content, are different, but their hash is the same. This is, if you think about it, it's not really trivial to generate such files, especially where you control most or part of the data. Now, what the researchers proved was that, yeah, they could actually create two PDF files or two JPEG files which have the same hash. So it's broken in that way. It's not broken in a way that it's actually like reversible trivially. It's not reversible trivially. At least I don't know of a public way to do it. So yeah, so it's kind of similar to MD5, though I guess like SH1 requires some more computation power. So going back to the topic, yeah, so what people actually decided to do is to make sure that a given message isn't tampered with. They decided to send the user two things. That is the public message and a hash of the public message. Let's say 1, 2, 3, 4, because why not, right? And then the user, when the user sends back the data it got from the server, it sends back it to the server and says, yeah, this is the data you gave me. The user is expected to send also well, the message and the hash is hash. Now, you might obviously point out that what does this give anyone? Because they can just, well, calculate the hash of this message and send it with it. So what does that give anyone? And it doesn't. And that's correct. So there's actually one more thing which I didn't mention. They actually calculate a hash of a secret value concatenated with the message. So the message goes here, and this is the hash. Now, they don't send you the secret value. By the way, this is like totally wrong and incorrect. Do not use HMAX like this, and today's episode is actually about this. But this is a way that we sometimes find being out there. Yeah, but the idea here is that we do not know the secret message and, the secret, and it's never sent to the user. What is sent again is only the public message, so this message and the hash. Therefore, if I would change the message here to like YYY, again, like I did previously, I have no way of actually recalculating the hash because I have no idea what the secret is. So I don't know what's the secret. How can I calculate the hash if I don't know what's the secret, right? So that's the idea behind HMAX. HMAC, yeah. So again, it's hash message authentication code or hash-based message authentication code. And this is a perfect example of how not to do it. How not to. Yeah. But okay, let's do an example, I guess, with our stupid hash again. So I actually could use part of this code. So let's assume that our secret, which we never tell the user, is going to be secret, because it doesn't matter. Yeah. So what we do is first we update, and let's say the message is like I told you before. So first we update it with a secret, and then we update it with the message, and then we get the hash. So what's the hash? The hash is 02. And now we get back the input from the user. So, yeah, like user message. It's, let's use the same message, and the user hash, which we got from the user. And it's, yeah, let's do 02, it like this. And now, when the server receives it, the server is going to do something like this. It's going to again calculate. It's going to put this, like, calculate a hash of the message it received. So it received the user message and finalize. Okay, and then it's going to say, yeah, like the digest is okay or it's not okay, right? So it's going to compare it to our user hash. So let's run it, and yeah, this case is true. But assuming I would want to change it to something else, I have no idea what to change it to. And if I leave it like this, I get false with a certain probability. Probability in case of my stupid hash is obviously like 2 to the power of 8. I can just guess it, right? But like MD5, for example, has 2 to the power of 128, and that's a really huge number. And you just cannot guess it. It's not guessable. It's not brute forceable, unless you have some other information. But let's assume it's not. And like if you are using like SHA-512, then 2 to the power of 512. 2 to the power of 512 is yeah. Let's just do this. 212. Yeah, it's like this really long number which goes like there and goes back. So I don't think they're like these many atoms in the universe. Maybe they are, but okay, so how long is the string? No, it's like 10 to the power of 155. So like 10 and like 154 zeros. So it's not guessable. Anyway, well, in this case it's guessable, but let's ignore it. So the question here is, assuming that Przemek asks, is SHA-1 secure for storing passwords? So Yes and no. It's not reversible, but I wouldn't recommend using a simple hash like that just to store the password, because it's calculating SHA1 is rather fast, and what you want to do when checking the password is you are okay with waiting. You are okay with waiting 1 second, for example, for the calculation to finish. And what you want to force the attacker who steals your database and wants to brute force all the hashes, right? What you want them to do is you want them to actually waste 1 second per test. Therefore, you do not use SHA1 itself. You use it in a function which makes it harder. For example, I was supposed not to touch this topic, but okay. Okay, so I'm going to basically tell you what Foxtrot Charlie is telling me. I'm going to add something to that as well. So yeah, there's something like password-based key derivation function, blah, blah, blah. Basically, the idea here is that this function takes a salt like a hash like SHA1 and then runs it, for example, 1 million times and like concatenates the result in some way. And due to that, you have in the end, like calculating the password, you have the hash, which is the same size, but calculating the password takes like 1 second, for example. And another thing which also Foxtrot Charlie did send me is, well, you can look at key derivation function here, is bcrypt or scrypt, which you might also want to look at. Oh, Niels Provost, I didn't know Niels did it. That's really cool. Yeah, basically the idea is again to do the same. As well as an example here. But again, the idea is to make the password calculation hash, the hashing of the password really, really slow. And this is what you want to keep in the database, a really, really, really slow hash. So don't keep SHA1 there, keep something slower, like for example, give bcrypt over SHA1 or like scrypt over it or whatever. Yeah. Okay, you might want to. Oh, scrypt is deprecated. Is it really? I didn't know that. Huh. Okay, did they break it? Yeah, I remember it's used in like it was used in Litecoin. So that's interesting. I don't know. Okay. I think the idea behind scrypt was that it was supposed to be not calculatable on GPUs. It required like a lot of memory to calculate the hash. I'm not an expert on this. Do read blog posts from people who actually know what they are talking about when talking about scrypt and bcrypt. So yeah, I basically just remember that I do have to use a slow hash, and this is a good rule of thumb. Yeah, so yeah, SHA1 isn't really the way we want to go with storing password hashes. Okay, going back to this. Now, let's assume, for the sake of a discussion, and this is a really important assumption here for today's episode, that the public message for us is we don't really want to change it. We are okay with keeping the public message as it is. But we want to append something to it. We want to say like public message something, and this is important, but this will be usually something, and like which we don't control, and then let's say the y again. Now the question is, how do we do that? Now, in this case it's okay for just y because our finalize doesn't do anything. If our finalize would actually call update, then we would not control some part of the data, but here we do. So how do we append anything and calculate the correct hash to it? Well, if you think about it, you already have the hash calculated to this moment, right? So what is stopping you from like putting this back in the register, like putting this back here, and then running update on it again, but only for the new data, right? Because for the old data, it's already there, it already has been calculated, but you will run it only over the new data. Well, actually, nothing is stopping you, and this is exactly what the attack is about. So what you can do is you can yeah, like create it again, but this time you actually override the registers with the hash. We know the hash is 02, right? So we override it. Yeah, it's probably, yeah, whatever. And now we call update on whatever we want to add. So let's say that the thing we want to add is y. Yeah, this is fine. So we do update, call on the thing we want to add, and then we call finalize again. Again, in this, our finalize doesn't do anything, but when we get to MD5, it does something. This is why I wanted to have the finalize already here, so you're not surprised that there's something like that. And yeah, and then you just grab the digest. So let's print it for ourselves. Let's do hex digest, and let's set the user hash to the hex digest again. And to the user message, we actually need to append the data as well. Okay, so I guess we can do this. Print user msg, print user hash, and okay, no. And yeah, guess what? The hash matches. So again, we weren't really able to do anything about this message, but we were able to append any data to that we wanted. And we were able to like grab this hash, which is of this message, put it again back in the register and run the function a couple of more times to calculate the new hash, take the new hash, and pass it to the server. So this is basically all there is. Now, in terms of this hash, because this hash is really stupid, right? It's in the name here. What you could do is you could actually even roll back the hash, as in knowing that the hash of the public message is this. What you could do is you could say, yeah, the like E, the character of E is what is like in hexadecimal 0x65, I think. So just take this 02 and subtract this from it, and obviously do it in an unsigned character like variable, in an 8-bit variable. And you basically got the hash up to this point, and then repeated with this, and with this, and with this, and so on, and you could get here, where you could basically do, after unrolling everything, you could put whatever message you like. So let's try it. This is, by the way, not possible with good hashes. With MD5, it will not work. With SHA1 or with SHA1, it will not work. With CRC32, it starts getting funny. So yeah, especially that this is basically, we know the plaintext, we know it. If we didn't know it, that's a harder thing, but we do know it. So I think actually in case of CRC32, you might be able to do this, what I'm going to do now. Okay, so instead of doing this, I'm just going to basically do like r equals 2 for I in range. Actually, no. For character in this to this, r equals r minus the value of the character, but again we are operating in an 8-bit register. And yeah, and now we have, after we do this, we basically have a hash from here, from this state. After the secret message, we have no idea what the secret message is. The hash will not tell us what the secret message is, but we can calculate it to, well, we can use it to calculate whatever now. So let's change the message to private y. Yeah. Okay, and we do need to do this again. This now override our register with our r and update. So sh update the new user message. And we get the we need to finalize it. We get the digest something, and let's see if it works. And as you can see, it works. So this is another attack which you could potentially do, but it's not what this episode is about, and that doesn't really work for correct hashes, which are not trivially reversible. Adding obviously is trivially reversible. Cool. So now we can get to why is this a big deal. Let's create an example web page in PHP, because PHP is the best language for, well, it's not, but okay, the best supervisor said that script isn't deprecated. He meant pbkdf. Yeah, that's a different thing. I think there are like a couple of versions of pbkdf, and usually what you're supposed to use is like pbkdf2. Okay, so let's start with the easy stuff, which is let's assume that we have a web page which, in case of an error, it redirects us to a page which displays an error. Now the error message, it's basically like this. If there's an error message, so if it's set some error message, I'm going to actually change this to get error. Okay, here we go. If it's set, then just display it. Let's do this. Okay, and just get it. This is not fully correct for multiple. Oh wait, whoa, what happened? Sometimes don't like when the compilers try to help me. I usually don't like it. What I would usually do here is like I would do and is string get, because in PHP you can also pass arrays, and it's not so bad currently. It was a little more funny back in the days. Okay, now the idea is that let's assume we are filling a form and we press submit, and the web page goes to some other page which processes the information and says that there's an error. So what it might want to do, it might want to do, well, basically send us a location header to redirect us, to redirect the browser to, yeah, like error equals incorrectly filled form. Now, and this is the implementation of it, so of just showing the message. Let's start PHP server. So I think I have PHP 5 here, but that's fine. Yeah. What do you mean invalid address? It's a perfectly valid address. Okay. Am I doing something wrong? Do you want me to do this? Okay, it wanted me to do this. So let's connect to that website. HTTP. Yeah. Okay, and now if we type error equals anything, well, it gets displayed, right? So in this example, let me do a space here. In this example, if we do this, then yeah, it just displays, right? But as an attacker or a pen tester, when you see something like that, you're like, oh, this is an XSS, right? There are also Livestream out with XSSs. So what you might want to do is you might want to do like, yeah, let's do the usual script alert 1 script. Okay, let's disable the protection. Header XSS protection 0, because yeah, so now it works. So yeah, again, if we are going with this scenario, what we want to do here is we want to actually put an HMAC of this error message here. So we want to have HMAC and a hash here, right? The hash would be not guessable, and the hash, if it would not be correct, then it would not actually get displayed, like the message would not get displayed. And let's assume that we, as an attacker, actually want to do that XSS var. We are going for like exploitation var, and we want to have an XSS var. So this will be our scenario. Now, let's assume we get here, and let's assume there's a secret, and the secret is unknown to us. So secret is going to be secret blah 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 something. The attacker doesn't know it. It can be as long as we need to. And now we do what's the name of the PHP? Is it just like SHA 512? Let's go for or hash, we can use hash. Okay. So actual hash is going to be hash when algorithm, what are the possible algorithms? 200, yeah, here we go. Let's go with SHA-512. It doesn't matter, but let's go with it. I'm going to switch back to MD5 probably later just to... So, no, let's do it like this. I'm going to go with MD5 and then I'm going to show you a real tool which you use on CTFs to do this stuff, because first I'm going to do it manually. Okay, so we give it the data. And the data is, yeah, the error message. No. Yeah. Why doesn't think that in the content of a string I want to write a function? And the we also need to check if there is the hash, if the hash is actually given. So if set, let's go to hmac, not hash, and it's a string. Okay, so if in these cases, so this is the actual hash and sent hash, like user hash is what the user sent us, is get hmac. Okay, and if it's yeah, if it's like if they don't equal, they are not equal, and I'm using the, yeah, remember to use this in PHP act. Then we do die a horrible death. Okay, here we go. Otherwise we do actually display it. So yeah, let's try it now. And it doesn't display anything because I probably have a typo in the code. It's the white screen of death, so-called. What is it? I guess it should show me an error. Invalid request, end of file. What? How is it an end of file? I don't know. I'm going to echo something else, like normal website here. I'm actually even going to add this. Yeah. Alright, normal. So yeah, that's fine. It didn't die. Oh, because I didn't pass. That's fine, because I didn't pass the hmac. Here we go. Like ASDF is still totally not a proper hash, so that's fine. So now let's calculate the hash of it, and I'm going to use a command line for that, because why not? So here we go, echo the secret. Don't do it in command line because you will store the secret in the history, right? And let's assume that we are going only for the incorrect field form message. Incorrectly field. Wow, really, I did type field there. Field, it's field, not field, obviously, form. Okay, I do need -n because I don't want the new line, and SHA 200. Or was I, what? Or was I going for MD5 now? MD5, so, okay. Here we go, this is our hmac, so I'm going to actually change this field form. hmac equals to this num, and it didn't work for us. I wonder why. Maybe I did a typo. I'm just going to copy paste this. No, that's fine, that's fine. Here, where I calculate the hash, I need to add the secret to it. Concatenated, here we go. Okay, yeah, and it works now. If I change anything in the message, right, so if I change anything here, well, here, then it stops working and I have no idea how to change the hash. So let's do the attack now on MD5. And to do that, I'm going to use an actual MD5 implementation, which is the OpenSSL one. Well, it's actually compatible with OpenSSL, but it's under public domain. It's written by Solar Designer, obviously. Who else? Solar Designer is like a really famous person on the security scene. He has been on the scene like forever and has his hands in like everything. Well, you can see like this implementation was written when I barely could code. So this is the implementation of MD5. I'm not going to go through it. What you need to know is that there are, oh, let me actually open this file as well, which is the interface to it. Here we go. So, yeah, as I mentioned, init, update, and final, or finalize, depending on the API you're using, right? These are the actual registers which are used for calculating the MD5. What you saw before on the screen is actually some magical functions which are doing the calculations. We don't care about them. And yeah, MD5 actually isn't a fully streamed hash. It actually takes blocks of 64 bits. 64 bits as in 512, sorry, 64 bytes as in 512 bits. And so it waits until you give it that much data, and only then it actually does calls the function to do the rounds which do the calculation, the updating of these registers. Now, if you like run out of data, like for example, I want to calculate MD5 of 4 characters, what happens there? And this is where finalize comes in, or final. Final actually is supposed to pad the data, if there is not enough data, to pad it with something, and if you pad it with something, then you have the 512 bits, which you can again do a final update on. And in case of MD5, I think it was like adding one set bit, then a lot of zeros and something at the end. So let's see what's that. So this is the update. Again, it's basically, well, calls I think the body only if 64 bytes are available. Now the finalize does, what do we have here? Checks how much data is used. Yeah, this is 1 followed by zeros, which I mentioned. And then it copies to the buffer. No, it sets the buffer to the zeros. And I'm pretty sure it does put something at the end as well. I don't see it in the code. Well, whatever. Let's see again. So it puts this. Yeah, I don't think it actually doesn't put anything else in the code. Well, that's fine. Okay, whatever. So, yeah, what we will have to do to this function. So again, if we have ASDF, then it's going to put one, well, x80 and then zeros until the end. So, and this is pretty important, because whatever data we have which is already hashed, we will need to append this to the end, because this is the state of the hash we know. Not here, because finalize was called here. So that's what I mentioned, that sometimes we have some uncontrolled data which we do not control, which needs to be added to the message which we want to extend. And this is what we are going to put there in case of MD5. So, and afterwards, we put the hash we know in MD5's register, and we basically start rolling again. So, and this is the registers, right? As I mentioned, so we are going to put the hash here. Okay, now I do have an application written which actually does that for a file. I do not care about the file. I do not care about hashing a file. I care about hashing my own data. Yeah, let's just like remove it. And yeah, I don't care about it. So, and let's assume for the sake of the exercise that we actually do know, yeah, we know this, we have this link, right? We have this URL, and this is all we know. We don't know the secret. Let's assume for the sake of the exercise that we also know the length of the secret. It doesn't matter, that we don't know it because we can brute force it. But given that we can brute force it, you know, like try length 1, length 2, length 3, length 4, and so on. Sorry. This is kind of dying today. Yeah, so given that we can brute force it and it's really easy to brute force, I'm just not going to bother at all. So let's assume we know the length of this, and the length of this is 27. So const length secret is 27 characters, and let me just note here that this can be okay. So now this is our message, like the error message. I'm going to URL decode it, because this is the form the hash is calculated from, and this is our HMAC. So I'm going to actually separate the HMAC with, sorry, each 8 characters. Here we go. This is fine, this is 8 characters, okay. So yeah, basically this is register A, register B, register C, and register D in MD5. Register as in, you know, the 32-bit variable, right? Yes, I'm going to use hash pump later on. Okay. So I need to initialize, well, create this track, the context of MD5. So ctx, here we go. And now I need to initialize it with the initial values. And I just pass it. What init actually does is it just puts in the registers, yeah, like random values. These values aren't random, like they're carefully picked by whoever created this. As you can see, this is like totally unpredictable. Yeah. 1, 2, 3, 4, 5, 6, 7. Anyway, that doesn't matter. Some values which are put in the registers, we are going to overwrite them in a second anyway. Now, we need to actually, well, get everything up to the state where we would be at the end of this message. So we know there are 27 characters in the secret. We could again brute force it, but I'm not going to brute force it because it doesn't matter. Let's go with an update here. Update takes the context, the data, and the size of the data. Okay. So the context. Oh, and now it's the data. Doesn't matter. 27 is the length I want, but doesn't matter what it is. Is it actually, because whatever I put here, I'm going to override the registers anyway. I want the other things to be the counters. I want the counters to be ready. So here we go, 27, perfect. And now I'm going to put in this. So const error, character error, yeah. So let's put this error and string length of error. Okay. Now I mentioned that, well, at this point, the original hashing algorithm called final. So we do need to also call final. I think that's the way we can go, but I don't want to call final. I want to actually add the padding myself, just to be sure it's correct. But I have absolutely no idea what's the size of well, I can calculate it, whatever. This is the length of 23. Yeah, 23, and this is 27, so that's 50. So up to this point we have 50 characters, and I did mention that we need at least 64, so that means that we are missing 14 characters of padding. So now let's update it with padding. And yeah, let's put x80, so that's 1 and 13 of this. So that's 4, 8, 12, and one more 15, and yeah. And now we are at the state where we need to change the registers. So this update actually did call already, did the math, so we can update the characters, I guess, sorry, the registers with our values. So the context A is equal to this value. I wonder if something doesn't work, it means that update didn't actually call, like, flash the data yet. Though it should have 64 characters in the buffer, it should automatically call it. If not, we are going to force it to do it. Okay, now we reset it to the hash we know, and yeah, what we do is now we extend it. And what do we extend it with? We extend it obviously with what do you know? XSS, right? So script alert 1 script, and this is 25 characters. And then we finalize it again. So final ctx, and then we where does final? Oh, so I need actually sound. Okay. Yeah, it puts the digest here in the result. So if you look at final, and let's do that. Let's look at final at the end of the final. Yeah. It basically just copies the registers to the result. And it's copying it little endian. Perfect. This is exactly what... oh, is it perfect? Or is it the other way around? Do we need to care about endianness? Yeah, we need to flip it. So how do we flip it? There's a function for that. Yeah, I'm just going to write a function to convert it. Okay, so it's a big endian to a little endian. Okay, let's see. So R0, and we get a byte, and then we take this byte and we shift it by 24. Okay. Okay, and here we do 16, 8, and 0, and here we go the other way around. This should... Yeah, I'm going to test this function. I don't believe I coded it correct. Sorry. Oh wait, this is actually Sublime, so I can do this. Okay. Cool. But I am going to test it in a second. So yeah, we update it, and then we flash it, and then we... Okay, let's see if it compiles, but I did mention I want to test it, so let's do printf x b to e, and now this is going to be the test function. Perfect. Now let's do gcc calc, and okay, MD5. Yeah, I could use like N to HL or H to NL, but I didn't want to play with importing, adding other headers. So yeah, I just coded it. Yeah, it works. 1, 2, 3, 4, 5, 6, 7, 8. That's good. So this is implemented correctly, and this is the new hash which we got. So this is the new hash. Now the question is, what's the message, right? So the message which we need to put in. So again, the hash is going to be this. And the message, so hmac equals this, and the message, so error, is going to be equal to this. But then we need to put this. So that's 80. And this 00 we need, this is 12 and one more. And now the actual message which we added, which is this. And this is the message which we give it. So the original message, the padding, and then whatever we wanted to add to it. And the padding we don't control. So this is why hash extension attacks actually don't work in all cases where there is an HMAC which is broken, because sometimes the data is parsed, and like a funny thing like a padding is found, is like an error is thrown. But in this case, it's just going to be displayed, so we don't care, right? Okay, so yeah, let's test it. I'm a little worried that Chrome will actually not like me putting binary data inside. This is, by the way, not going to work. I mean, yeah, I don't think it's going to work. Yeah, horrible dev. There might be several reasons why this happened, but to debug it, I'm actually going to cheat a little, and I'm going to display the error just to know like what's inside. Okay, so echo. Okay. No, it's actually, I think it's fine. Yeah, looks fine. It actually did pass correctly the zeros, which I was afraid for. Which means the problem is somewhere else. So as I mentioned, if the problem will be somewhere, it's going to be here, but update doesn't actually flash it before we do this, right? So we can check it in a rather simple way. Let's do here, let's check what's in the registers. Okay, and we do this. Okay, and we then display it again after each update here, and I guess here as well. So let's do this. No, wait, this is not my console, this is my console. Yeah, it actually did update something, but I have no idea where I am at. So here, okay. Let's do this just to have this. Yeah. Okay, so no, it did update, so this is fine. It did update, then maybe, just maybe, I didn't have to do this thing. Let's assume I didn't, so let's assume I just do return R here, and let's see if that works. Yeah, maybe I played myself. So I'm actually going to move this, like minimize it. Okay, and this is the new hash which got calculated. Let's try it. Move this hash. And still nothing. So, what we can do now is we can... I'm actually a little worried about this padding. Let's go to Wikipedia and let's look for MD5 and let's look what they say about the... no, we probably need to go to RFC, yeah. Okay. Yeah, I think this is the MD5 RFC. So 1, 3, 2, 1, and this is basically the specification. So let's see what they say about the padding. Appending padding bits. The message is padded to its length, which is this. Oh wait, blah blah blah. But is the message is extended? So yeah, I got the padding incorrect. 64 bits shy. We leave the 64 bits at the end. Padding is always okay. What do we do? 1 with zeros, okay. And what do we do with this? Append length, yeah. I knew there was something like this. Is it little endian or is it big endian? Yeah, I was pretty sure there's something like this here. Okay, let me uncomment this again. So this is actually doesn't change too much. We just need to change this. We need to remove the last 8. So 1, 2, 3, 4, 5, 6, 7, 8. Here we go. And here -8. 14 -8. This is pretty complicated math, so I will probably fail it. Okay. And now we need to do length. I don't know if it's going to be big endian or little endian. I don't know if I care. Let's assume little endian. And sign long long. That's 64-bit. Length. Okay. Now the length is, well, we know the length is 50, right? Or was it? Append length of B, length of the message before padding B is what was added, so that's 50 for us. Is appended, unlikely that is greater than only lower, that's fine. As two 32-bit words appeared in low order word first, in accordance to previous conventions. Does that mean little endian? Okay, let's assume it's little endian. So this is fine then. Then what we do here is we do update on the context, and we just pass length to it. And that's the size of 8. Okay, perfect. Now let's do this. Let's try this hash and... Oh wait, something didn't work. Because it's the same hash. What? Okay, so... What? I see you're suggesting on the channel that it should be padded with 31, but no, the padding is in bits. So if we go to padding bits, it actually says that a single 1 bit. It's not 1 as in character, it's 1 as 1 bit. So this is fine. Like this is fine, this is all correct. Now, the length is updated. Why didn't the hash change? Did I mess some calculations up? Oh, wait, it did, and then... Or didn't the hash change? Let's see. Maybe it did, but only... No, it didn't. That means I'm failing something. This is fine, then I updated with this. Oh, wait, oh, right, because this... no, that's almost fine. Here, I need to put it in the message as well. The hash is fine. The message is not correct. I do need to display this. And it's little endian. But that's 50, I mean... It's in hexadecimal 30... 30 what? 38? I don't know. Python hex 50. 32, okay, I failed, but sorry. So 32 is going to be put in little endian. Not here, not here, not here, not here, not here, here, 32. Okay. And let's see if this works, because yeah, the hash is correct. So not the hash we have a problem with. Okay. It's better. Did I? Oh, I didn't comment this out, so let's do it once more. Thank you, Dashin, for pointing this out. And now I hope it's going to work, and it doesn't. Below. You know what? I'm going to basically check what padding is actually adding. So when finalizing, right? So, okay. This is the final, yeah. This is adding the the size. So yeah, and the size is okay, it's 50 for us. Unless I get something wrong. Let's check it once more. This is 27 characters, that's correct. This, so we know that's 27 characters. This is 23 characters, that is also correct. Let me double check here. 23 characters. I'm pretty sure that's 50. So that's the end of the message. Now we put (42 by 3). 42 by 3. 14 characters, so 50 plus 14, 64. This is okay, and this is where the new message starts appearing. Now 1, 2, 3, 4, 5, 6, 7, 8. This is also correct. At least I think it's correct. Okay, so let's do like this. For and I equals 0, I less than 64. Let's just output the buffer because I'm really curious what happens there. X ctx buffer. Oh, it's actually, you know what? I don't have to do it here because it's nice enough to. I think it's nice enough to not change the buffer, but yeah, let's not risk it. Debugging 101. This is the buffer. Why did it? Is it in bits? Is the length in bits? If the length is in bits, then I need to put something else there. So 50 times 8, which is 400, which is hexadecimal for 0190. Okay, let's assume that's actually the case. So that means I'm going to put 9001 here. And let's try again. Yeah, it worked. So yeah, we got it. Basically, my mistake here was that the length was actually in bits and I did give it the length in bytes. So it was 50 bytes, but 400 bits, or 190 hexadecimal, as you saw. So that's basically how you implement it by hand. Now, on a CTF, you do not implement stuff like that by hand because there is no time, unless there's some new hash which you never saw before, obviously. Therefore, what you use is hash pump, which I did mention before. Oh, by the way, if you look here, it's like this thing has been displayed, right? But apart from that, like, nobody cares about this thing. Everyone cares about this thing, which still gets correctly interpreted as HTML. So the hash length extension attack basically is content dependent, as in some context dependent. In some contexts it will work, in others it will not. Now, if we want to grab a correct tool, hash pump is, I think that's a bwall hash pump. I think that's it. It's actually a really nice tool that you can use. I think I did use this one before. Yeah, let's just do this, what they say here. Okay. Make, cool. Okay, and we have hash pump ready. So what do we pass it? Well, we need to pass it, you know, all the same things again. The question is only what exactly do we need? So what we need is, we need the signature test, what is run test. No, we don't. The signature from the known message, the data from the known message, the additional information you'd like to add. So this is our XSS payload. and the key length, which again is brute forceable, so I'm going to just put it 27 here. Otherwise you just try like 1, 2, 3, 4, 5, 6, blah blah blah, 26, 27, and it will work at some point. I think the data here can be hexadecimal, or can it be? It doesn't matter. It actually just displays this, so that's fine. So let's do it, and let's go back to here, where we had the HMAC for this. I'm going to copy the HMAC. Here we go. Then we need to pass it the data, which we do know. The data is this. So let's copy the data. And URL decoded, because it's obviously the hash is calculated after URL decoding. So here we go. And now what do we want to add to the data, which is again the payload, which is, oh, maybe let's do K27 now, and now the additional data, which is the exercise payload. For the sake of the exercise, let's just, let's do alert 2. So let's change it to 2. So the hash is different. Here we go. Okay. Incorrectly filled form, blah, blah, blah. This is it. So, yeah, I guess I can just copy it here from here. Here we go. And the HMAC is here. This is our HMAC. Yeah, like in all honesty, I thought this is an error message when I, like, after you run it, but it's not. And here we go. As you can see, like, I changed only 2 to 1, and the whole hash is like totally different. And it works. So yeah, this is what you do on a CTF. You basically run hash pump with a couple of arguments. But I guess now you know the theory behind it, like what's actually there and what you have to do. So I guess that's it for today's topic, which means I can answer a couple of your questions, and I will obviously submit the code which I've written today to GitHub, as usual. If you don't know, I do maintain a repository on github.com, ginveil, and streamn, this one. Yeah. What is this? Oh. Click for language details, it will show me. ROF. What is ROF? I have no idea. Okay, that's funny. Yeah, and I will just upload it. Upload it here under eFail. And if I don't do it today, then I'll probably do it tomorrow, so there's that. Let's do questions. Is there any question? Yeah, there are 10 questions. So the questions will appear here. Here we go. Or do people actually... this is, I guess, about the open source versus closed source security. Mindshredder writes, or actually people do think that somebody is looking at it. Yeah, that's also a risk, right? Yeah, you never know. Use Let's Encrypt org plus some cron tasks to refresh a certificate is free. Yeah, I know, I have a little more complicated situation for that hosting, but I'll probably either go with Let's Encrypt or something else. What do you think about PeerTube? I have absolutely no idea what PeerTube is. PeerTube, trending videos. PeerTube, join PeerTube. PeerTube is a software that you install on a web server. It allows you to create a video hosting service, so your homemade YouTube. Oh, cool. The difference to YouTube is that it's not intended to create a huge platform centralizing videos, blah, blah, blah. On the contrary, oh, so it's like a peer-to-peer network where you host other people's videos and they host your. That's cool. I didn't know about it. Thank you for sending me a link. This is basically the website. Cool, that's cool. I didn't know about it. I'm going to take a look later. Do you really have such problems with your... What? With my what? What? Esophagus, what's that? food pipe. Do you really have such problems with your esophagus? I don't seem to remember having any problems with it, so hopefully. Yeah, why do you say I do have? That's a good question. Thank you, Pavel, for the donation. Thanks. Better 90 minutes here than watching PL national football team. Okay. Thank you for the compliment. Okay. Push AD writes, "Hi, I joined in the middle, and also I have a question. Do you have any clue, by curiosity, I'm asking with no knowledge about crypto, is the known crypto used RSA AES are safe, like ISPs can read plain text? I think RSA is mostly safe if you use the proper key size, at least I don't know otherwise. And IES is, again, it's safe, and I don't think there are any attacks which work on ISA. AES, sorry, on AES. That being said, I don't think people recommend using RSA. They use like the curves usually, like ECC. Yeah. So yeah, RSA, as far as I know, is still safe. There are quite a lot of funny little attacks on RSAs, but they are working only if you actually like really scrub the implementation of RSA or use it incorrectly. Did you think about podcasting? It would be interesting to listen to you on iTunes. Yeah, I actually did think about it, but the stuff I talk about is usually technical, and it requires me to write some code, show some, like, draw some diagrams and so on. It probably wouldn't work for, like my topics to do it without the video. That's my feel, at least. But I guess if I would be talking, like about coaching stuff or whatever, then that's the different thing. But I'm not, right. I prefer technical stuff. Przemek writes, do you think there will be more secure bugs due to speculative execution? Sorry, more security bugs due to speculative execution or due to other CPU architectural details? Well, for now, there will be a lot of bugs showing up about, due to speculative execution, right? For example, there was a message on, I think, security disk. Sorry, what was the name of it? Like open source security, OSS security? Yeah. From the OpenBSD folks that they disabled hyperthreading because they heard that there is another bug coming up, and there's like the question, like, what's up with hyperthreading? So, and there was the floating point register leaking between processes due to speculative execution 2 weeks ago released. So speculative execution is the new hotness and is currently looked at by many people. Therefore, I think we will see a lot of bugs coming from this direction. Now, afterwards, we'll see. Maybe there will be, like, somebody discovers another avenue of bugs and vulnerabilities in the CPU, so we'll see. But for now, it's the year of speculative execution. How would computers be like if there would be no ACPI? ACPI, what was it? Advanced Configuration Power Interface. I guess you can answer that question by looking at computers from 91, 92, 93, or 94, or like these years, right? There would be like pretty... I mean, things work back there fine. Unless you want some other answer, but I'm not an expert on ACPI. From Noodly, can you estimate the size of private SSH key that newest supercomputer 200 petaflops in USA can crack in a week? No idea. I'm not too deep into cryptography, so no idea. You probably should ask that question to somebody who is like deep into cryptography. And also, yeah, like, you know, SSH private keys could be both RSA or could be like ACC, I think, as well. So depending which one do you think about, are you thinking about? Is that true that web application shouldn't tell the user the username, that the username is good but password not? It's a good question. I saw that discussion which we are referring to, but yeah, because like historically everyone said that, yeah, do not, if somebody enters the user and the password, do not tell the attacker that the user exists or user doesn't exist, because that reveals some information. And then there was an article claiming that that doesn't really matter, because there are, like, for example, other ways to determine if the user exists. But it depends on the context, I think. I mean, and do refer to that article, because probably the author actually had more interesting stuff to say than I just did. But from my perspective, it doesn't really matter. I mean, it's hiding like some information, but not a lot. And usually there are other ways to figure out if a user exists. So I don't have any hard opinion either way. Is SHA1 HMAC also streamed like MD5? So SHA1 is also like that, and so are like the SHA-256 and so on. Now about the Mac, let's actually switch back to the desktop, because I didn't tell you in the end how to correctly do it. So you can look on Wikipedia, but actually instead of looking on Wikipedia, look at the libraries which you already have if there is an HMAC function, because that's usually the correct implementation. For example, PHP has an HMAC function, hash HMAC, which is, I hope, is actually correctly implemented HMAC. Otherwise, if you look on Wikipedia, there are like, yeah, this is the way from the RFC, which is what you do, H here being, for example, SHA1, right? So you calculate, you have some like padding, and K, I have no idea what K is, the secret key. And iPad, I don't know what's an iPad in this context. It is probably written down there. This is usually denoted for XOR, and you concatenate it with a message at the beginning, and then you concatenate this hash, which is at the end, with again the key and OPAD, whatever that is, like probably some other padding, and you calculate the hash of it once more. So yeah, so there are two hashes, and the message is actually like the secret is. As you can see, basically on... is this correct? The idea is that the secret could be appended at the end of the message as well, but I think it's not appended here at the end of the message, but that's fine. Yeah, look on Wikipedia anyway, because there probably is some... Oh yeah, this is what I was going after, like... sometimes you want to append the key at the end as well, but yeah, don't use it, because there are like some papers which say that this isn't great either. Now, I don't think there is something like SH1 HMAC by itself. Usually if you write like HMAC something, that means that you are using one of the ways to mingle up this function to create an HMAC. Yeah. HMAC X, where X is the hash function. Anyway, yeah, it's also, if you look at the page, sorry, for hash pump, which I did close. No, I didn't. Here we go. It actually lists the supported algorithms and somewhere. Oh yeah, here we go. So there's like MD5, SHA1, SHA256, SHA512 as well. I'm not sure. Oh, and CRC. I'm not sure about other hashes, if any other hashes could be used to that, but these are the most popular hashes. So yeah. So that's that. Why we can't hash a password 1000 times with SHA-256 to transform a password into an AES key? Yeah, we can do that. I mean, Oh, you mean to create it into a AES key? Well, first of all, depending which AES mode are you using, but I guess you're thinking about AES 256. I mean, I think you can do it. Please correct me in the comments if I'm mistaken, but I think you can do it. I think that's one of the ways you derive a key from the password, because a password is basically something a human can remember, right? But algorithms like AES for cryptography don't use passwords, they use keys. Keys being something which has a proper length, like for example 128 bits or 256 bits. Therefore, you need to take the password and somehow create the key from it. And I mean, using SHA-256 or another hash is a pretty default way to do it, I would say. But again, please correct me if I'm wrong, because I am not 100% sure about it. And this is something I never checked, actually. Which antivirus do I use? I probably chatted about this a couple of times already, but I don't use any antiviruses. They are useful for some people, and they are an attack surface for other people. So yeah, I consider myself being in the group where it's an attack surface. Antiviruses do a lot of data gathering, especially files. What do you think about it? It makes sense. I mean, I wouldn't look for on the topic of it like they're stealing our files. They're trying to get suspicious files to be analyzed, to be added to the signatures in a little more preventive way. I'm pretty sure like the sane antiviruses have a way to disable it. And so I understand why they are doing it. Is it something they should be doing by default is a different thing. And in the end, it's up to the user to agree to it, right? But in the end, antiviruses are just like, huge parsers and a huge attack surface. So yeah, I'm a little worried about them. ROV is some ancient thing, and GitHub is classifying repo as ROV because you have a big dump file with a .3 extension. Okay, thank you ABC for explaining. That makes a lot of sense. How to prevent hash length extension secret after clear text check if clear text isn't extended? Well, you cannot really check if the clear text isn't extended unless you add some length at the beginning of the clear text, for example. Apart from that, as I already shown, you do look in the Wikipedia on the HMAC function, how it's correctly done. Is pre-image attack a rainbow table? No, a rainbow table is an optimized way to store databases, a database of pairs, pre-image and hash, in a way where you sacrifice some computing power in order to store more hashes. Basically, you actually don't store all the hashes. You rely on being able to compute to do some additional computations. But yeah, basically, it's a really interesting topic, rainbow tables. But it is used for pre-image attack, but it's not a pre-image attack itself. It's basically like a data structure, I would say. But yeah, you're not far off, basically. Are there any open source modern CPUs? Yes, RISC-V. RISC-V is open source. It's pretty awesome, actually. It is written like RISC-V, but it's actually RISC-V. Yeah, pronounced RISC-V. Yeah, it's open source. You can read the architecture. You can basically get from the internet the cores for FPGAs to load your own RISC. And I think there are some what is it? Hive RISC-V or S-Hive. There's a CPU which you can buy. Yeah, Hive. That's it. Yeah, you can get some from C5. You can get well, it's an early prototype motherboard. Let's call it like this, with a RISC-V CPU. So yeah, they are, and it's actually pretty cool. And I think like I read somewhere about, for example, like NVIDIA is starting to put RISC-V CPUs on the graphic card to handle the firmware stuff, you know, non-graphical communication stuff, which is cool. So it's getting adoption. Let's go back here. Are there any mitigations for jump-oriented programming? In all honesty, I don't remember the topic of jump-oriented programming too well. I read the paper when it came out, and that's about it, so no ideas. And the last question, why is XOR used so widely in cryptography? Why not or AND or some other math operation? Because both OR and AND are not, well, have different properties basically, in a way where XOR, if you XOR something with a value twice, you get the same thing as at the beginning, and that's not true for AND, and that's not true for OR. And so basically XOR is reversible, and 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 OR are not reversible, so they cannot be used in the same manner. Instead of XOR, what you could use is, for example, addition, which actually on bit level, XOR and addition work the same way. They give the same exact results. At bit level, I mean when you have one bit. Yeah, I can just show you. So that's why XOR is like plus in a circle. That's why it's denominated like that. Okay, let's just stop here. So if we have p, q, and then let's do p plus q, assuming again 1-bit variable. So 1-bit variable. Let's do this. And then p XOR q, or XOR, however you want to call it. I just say XOR. So 1, 1, 0, 1, 1. Okay. So 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 0 is again 1. And 1 plus 1 is 10 in binary. But we are only talking about 1-bit variable, so 0, right? And if you look at XOR table, it's exactly the same thing. So yeah, in this context, addition could be used as well. Addition is nice because it's reversible by using subtraction, right? So in homemade cryptography, you might also find like encrypting using adding something and decrypting using subtracting something. Apart from that, I don't think there are any other interesting reversible operations which are worth mentioning. In obfuscating code, what you sometimes find is bit rotation, because bit rotation is also reversible, but I'm not sure it, well, it can be used in a manner where XOR can be used. So basically that's it, because XOR has nice properties, as in is reversible, for example, right? Do you plan, there are 2 more questions by the way. Do you plan a stream about security scanners or mechanisms? How to improve security, sorry. My voice is dying today. To improve security inside a team of developers, or do you have any pointers to good literature? No, not really. I mean, I'm not a huge fan of automated scanners, security scanners, and so on. I rarely use them, and they are there only to find low-hanging fruits. And they are good at finding low-hanging fruits, but they don't find all of them, and in the end, if you rely only on them, they provide a false sense of security. So I'm not a huge fan. But that being said, do use any scanner, any static analysis tool which you can find, which actually finds bugs and allows you to fix your code. Do it. I mean, there is no reason not to. But do remember that this is not all. Like, there might be more bugs. So do practice like defense in depth. Do practice privilege separation in your design, and so on. I do not have any good pointers to good literature. Sorry, no idea. Maybe someone on chat, but I don't. So yeah, sorry. I know my answer isn't the greatest. Okay, let's finish with this question. Do you like new copyright law, Article 13, 11, 3, and so on? Yes, the new law in European Union. I don't like it. Obviously, it's too wide. I'm kind of happy that I don't live in European Union. But that being said, given that I'm I have a passport from a country from the EU. Yeah, I don't like that. And also, like as a book offer, right? I don't like the new law as an offer. So let's hope it doesn't get passed in the way it currently looks. Yeah, but I'm not panicking either, as usual. So thank you, that's it. Today's moderator was Foxtrot Charlie. Thank you, Foxtrot, for your help. Thank you, everyone, for coming, and see you tomorrow if you speak Polish on the Polish live stream. If you don't speak Polish, then well, you can come anyway. But in all honesty, see you next Wednesday, and we'll chat about address sanitizer then. So that's it. Thank you. Have fun on this weekend's Google CTF, and enjoy the rest of your evening, day, whatever time zone you're in. See you.
the whole